Section 6.1 is an introduction to polynomial functions. So the general form of a polynomial is given below. And just to make sure we're reading this notation properly, all of the a sub n minus 1, a sub 2, all the way down to a0, these are what's known as the coefficients. So these represent actual real numbers in the polynomial. The subscript on each of these corresponds to the power of the x value in our polynomial. We call the first term a sub n that is attached to the highest power of x, we call that the leading coefficient, and n, the highest exponent, is what's known as the degree of a polynomial. Now the first four polynomial functions, degrees 1 through 4, actually have special names associated with them. So a polynomial of degree 1 is a linear function. Degree 2, we call that a quadratic function. 3 is a cubic, and 4 is a quartic. And so it's important that you know these names because when we're doing functions in the calculator, they're actually labeled by their name as opposed to their power of n. Now quadratics, we're going to talk about those first. They actually have some special properties. So quadratics we've been working with for a long time, and the highest power of the exponent is 2. It's the graph of a parabola. And the leading coefficient a actually tells us some important information about the shape of the parabola. So a parabola by default, just x squared, right, the simplest one, opens up. So when the leading coefficient is positive, the parabola opens up. When the leading coefficient is negative, the parabola opens down. We call the turning point on our parabola, we call that the vertex. So when the parabola opens up, the vertex is down here. We usually use the letters HK to represent the point. And when the parabola opens down, the turning point is here. We can find the values of the vertex using algebra, and to find the x-coordinate, we use negative b over 2a. So we just plug the coefficients into the formula. And then once we find the value of h, if you plug it back into the function, the y value that comes out will give you k. The domain on a quadratic is always going to be all real numbers. And the range of the parabola, well, if a is positive, remember the range are the y values, we can see it goes from the y coordinate of the vertex up to positive infinity. If the leading coefficient is negative, then the range starts down at negative infinity and ends on the y-coordinate. And notice here that we have brackets because that y value is included in the range. When we talk about the zeros or the solutions to a parabola, it's any values of x where f of x equals 0. And so there will be at maximum 2 possible values, and those are also known as the x-intercepts. So if you're asked to find x-intercepts, zeros, or solutions to any polynomial, those are all equivalent questions and statements. We write set the function equal to 0 and solve for the places where it intersects the x-axis. In the calculator, it's the zero function is usually what we look at. So our first example, we have a parabola, and they want us to find all the x-intercepts of this parabola. So on my calculator, I'm going to go to y equals, and I'm going to type the parabola that we've got. So it's 2x squared plus 17x minus 35. So I'm going to graph this. This is my, don't really see what's going on here yet, so I'm going to zoom standard. That's negative 10 to 10 on both the x and y axis. So we can see the parabola is dropping down somewhere over here, right, and coming up somewhere over here. So I can see one of the x-intercepts, but I can't really see the other one. So I'm going to go into window, and I'm actually going to widen this out so I can go back a little bit further. So let's try going back to 15. And I'll just stop the x-axis at, let's say, 5. And so, see, I can see both intercepts now. Now, remember, if once I've got the x-axis where I want it, if I go back to zoom and go all the way to the bottom and zoom fit, it's going to adjust the y values while leaving the x values intact. So now I can actually get a much clearer picture of what this graph looks like. So in order to find the x-intercepts, I want to find the zeros of this function. So notice here there are two of them visible on the screen. So when I go to second calculate and I go to 0, it asks me for the left bound. So I'm going to say -15. That's the left edge of my graph, and puts a little arrow over here for me. And then I can see that the other intercept is on the other side of 0, so I'm just going to use 0 as my right bound. But technically anything in here would work. So we can see we get another arrow here. So it's only going to check for zeros between these 2 points. So when I hit enter, I can see that my 0 is at -10.21. And I'm just going to take these numbers out to 2 decimal places, but make sure on your exams they're usually very clear about telling you how many decimal places to go out. All right, so now I'm going to try to find the second 0. So I'm going to go to second calculate again. 0, it's going to ask for my left bound, so now I'm going to start over here at x equals 0. And my graph ends at 5, so I'm just going to go all the way to 5. And so now it's going to check for the 0 that's here. So when I hit enter, I get x equals 1.71. And then we're asked not only to find the zeros, which we've done here, but it says write the factored form of the quadratic equation. So when we factor this, we actually have everything we need. The a value stays out front, and then, oops, a little equal sign here, and then we write our factors. So if this is x equals -10.21, I go minus 10.21, so it becomes a plus, times x minus 1.71. So this will actually work with any polynomial that once we find the zeros, we can write its leading coefficient out front and we just multiply all of the individual zeros. And it's always of the form x minus the answer. So any negatives will turn into pluses like so. All right, then it asks us to find the vertex. So we could use this algebraic method up here. It's a little bit long, or we could use our calculator. So in this case, since the parabola is opening up, the vertex is a minimum. So that means when I go into my second calculate, I want to scroll down and I want to pick the minimum of the function. So once again, I have to put bounds. So I'm just going to pick the bounds of my window. I'm going to check it from -15 all the way over to 5. And then it asks me to guess, or it says it'll guess for me. And I get that the minimum is at -4.25. So for the vertex, it's typically implied that we want the full point. So it was -4.25, and its y-coordinate was -71.13. So that's why I needed to zoom fit this function, so I could actually kind of get a look at the whole thing, so I could capture this minimum. It would still capture the minimum for you, even if this is off the screen. The calculator will return y values you can't see, but it can never return x values that you can't see. All right, so then we want to find the domain and range. So for parabolas, this is really easy. The domain of any polynomial is all reals, so that's pretty easy. But for parabola specifically, I know that the range is going to be from its minimum value, right, or the k value of the vertex, up to positive infinity. So this was the range because our parabola opened up. If our parabola had opened down, we would have chosen this form of our range. Then we want to find the intervals where the function is increasing or decreasing. So we've already determined that this parabola opens up. So when we read it from left to right, it's decreasing until it hits the vertex, and it's increasing after that point. So when we write these intervals, we always write them in terms of the x values, not the y values. So this function is increasing from the vertex, which is -4.25, that's the x coordinate, all the way to positive infinity. So from here all the way to here. It's decreasing from -infinity all the way to that x coordinate of the vertex. Notice I don't include the vertex in this case because it's actually turning here, so it's not really increasing or decreasing at that moment. And also notice that my intervals of increasing and decreasing covered my entire domain. So I've accounted for all the possible x values. Then we want to look at the concavity of the graph. Well, with a parabola specifically, the leading coefficient tells you the concavity. So if the leading coefficient here is positive 2, it opens up, which means the graph is concave up, right, everywhere. So they didn't ask for an interval, but the interval of this concavity would be negative infinity to positive infinity because it's always concave up. And I was able to do that by just looking at the sign of A. So only quadratics can you kind of take some of these shortcuts with.